Yeah, Viveka, tell me, you have raised your hand.
Ma'am, try to solve related assignment questions, ma'am, because we are means
Yeah,
today
yeah,
we are
yeah, yeah.
facing.
Today we
Yeah.
will be solving. So, what happened in the last class? Like, you,
Yes,
last
ma'am.
assignment you were not able to do?
Yes, ma'am. So most of the questions are not related to the lecture videos, ma'am. So we are facing too much difficulties.
Okay, okay, okay.
Try to like that can change the problems to try to solve these
Okay,
problems,
okay,
ma'am.
okay. Actually,
So much
okay, fine, fine. Actually, the problem is we are restricted not to solve the problems exactly of the assignment. But yeah, we can solve the problems related to assignment question. That is for sure. So today we'll be solving. So how many lectures you have watched till now?
I watched all lectures, ma'am, but this week also very difficult. Means all questions are unrelated, related only, but somewhat extension of problems like we are seeing dimensional of n minus one, like differently susceptible. So many things we are seeing this week
Oh,
session, this week assignment. So every
this.
problem having different,
Okay,
not
okay.
not there in our lecture videos.
To
Like
summarize, I think the lecture videos concentrate on the theory and
Okay, okay.
problems
And the
are
problem solving. Oh, okay, okay. The actual thing, like how I basically solve. So I take the lecture video concepts and then try to remember that like what are the some concepts, what are the some basic things that we have learned. Then after that, applying to the previous year problems. Like if I open my problem now only, so you can see. This is NPTEL assignments 5. These are some of the questions based on the Frobenius norm. Then I have to check like what is the this year problem it is. Then which of the following is false? Condition number. So hope you if you have seen that video based on condition number, then what is that condition number? This is basically what is the values. So we have to think with this. Refer to lecture number 25. Then what is the two norm? These are some of the questions. If I open,
ma'am,
yeah, yeah, tell me.
this type of PDFs I have, ma'am, every week last year. How we can get, ma'am, assignment questions last year's means not last year, 2 3 years.
2 3 years, okay. Actually, Viveka, 2 3 years, I have to ask them like, how can we get? But every year they are revising the concept, they are revising the course. So I don't know whether we are able to, we will be able to access 2 3 year question papers or not. But last year only we get access, I feel. So otherwise, if I would have access, then we can have problems from that thing, then we can solve the related questions. Wait, I'll check the SWAYAM portal. Like, wow, this year problem. You are telling it's little difficult.
Yes, ma'am. I whatever given reference book, ma'am. That also I downloaded, but not there in that book. Also, this type of questions like
O-
examples. In
Okay,
theory, sir was lecture in the lecture theory only telling, not examples telling, ma'am.
okay, 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 okay.
finally to solve the assignment of week 4. I had to listen to YouTube, you know, from other sites like YouTube videos of that topic.
Okay, LU decomposition and this thing, no, QR decomposition. So basically, for QR decomposition, you have to solve through this, what is it, Gram-Schmidt criteria, and LU decomposition, you have to learn specific ways. Today, I can tell that thing. Like if I am
Today you tell that then we'll be going to assignment of week 4. No? You should help us to solve week 5 assignment today.
Yeah, yeah, yeah. Week 4, 5 only. Today I am prepared with the week 4, 5. But there were students, some students that they were telling that we are having some difficulty in week 4 also. Like what is LU decomposition? So that LU decomposition, then you have to write the L in the form of minus L in the upper triangular matrix that minus L31, L3, L32 like that. The for specific formula is there. So if I'm just sharing the screen now, If you can see my screen, then do it. So to show it. Are you able to see my sound portal?
Yes, madam.
Okay, yes. So if we go to, how many of you registered for the exam?
I have registered.
Okay,
Like to have registered, ma'am. It is credits code for final year MSc.
okay. That is mathematics department. So this is reflector matrix, then this is reflector matrix, then Frobenius norm. This is V space. Okay, this is what is a condition now. I think Viveka, if we go through the lecture properly, then we will be able to solve question number 10. Then
Yes,
let
ma'am.
us
10 is okay, ma'am.
okay,
10
let's
is I
go one
understood.
by one, okay? Let's go one by
Yes,
one.
ma'am.
Then we will solve some related question as you are saying in week 5. Okay. Then let us consider a system of linear equation ax equals to b. They say
9.
this is what will the condition number of R2 using the Frobenius norm. So R2, so there will be again a formula, right? This is mod of AF into mod of AF power minus 1. This is, I'll tell you, this will we can also solve for sure, okay? This we will able to solve. I hope this is very easy. That is max by mid max. We will see what is the exact thing. Okay. And then let's see this. This you remember what is the formula for this using Frobenius norm. See this Kp is
Skin.
is given by this thing.
Frobenius. Ma'am, here Frobenius formula I know, ma'am. But here they're asking upper triangle, lower triangle.
Yeah. They are asking for the
You.
rotation matrix. Uh, you remember
But
that in rotation matrix only you will have a circle that transform to the circle. Okay. And
ellipse.
yeah, no, that's what I'm telling. In case of non-rotated matrix or non-orthogonal matrix, that will transform to ellipse. Okay, but if it is a rotator or a orthogonal matrix, that will transform to circle only. So that will have what? That will have inverse as transpose. That's why it has this particular property. We will see this question. I think we will be able to solve this also. Then if we see this, a condition number represent how susceptible a matrix is to round off errors. The condition matrix. Okay, we saw in the lecture itself that a round off error thing is given by how much? Condition number, right? This less than equals to condition number of that particular thing. Then which of the following conditions must satisfy? The be satisfied for P to be ill-conditional matrix. So what was that? Determinant should be greater than or equal to 1 minus 0. I think 1. Because determinant should be greater than or equals to at least 1. We had that condition. We will again see that. Here, again, it is based on condition number only using the properties. So here, if we see, I agree that you people have used to have some doubt whenever this term reflection, rotator, these things comes into the picture. So don't assume that reflector or any rotator is a different matrix, but it is a matrix which is a orthogonal matrix that reflects one particular vector to a uh, over a orthogonal space. So we will see what is that reflector also. Uh, what is the condition number of the reflector matrix? Again, we have to just find the formula which is used to reflect these things. So as we know, condition number for this all the orthogonal matrix is 1. It should be as we know that the value of the determinant of the conditional matrix should be greater than or equals to 1. But in case of orthogonal matrix, it is almost like it is rare minimum. That's why it should be 1. Or this is looking very tough. Let's see. This is one norm, infinity norm, Frobenius norm. Okay. So we have to calculate it. We can calculate. I think that is fine. Vivek, this thing.
If any concept is not clear, for example, I was also not clear with QR decomposition. Then I've come to know that QR decomposition is very much related to Gram-Smith orthogonalization. So that way you have to explore. And I think it is not proper to discuss the assignment question here. Anu madam can always solve the previous week assignment question with us. She can give us the details about previous week question, but I think it is not proper to discuss the assignment question directly. The course
Not
is doing very good.
means it is how question relating. I am telling only we are facing difficulties. How question related?
Actually, yeah, but I think Vivek, what I think,
Yes, sir.
it is not fair to disclose the question when it is given as an assignment. It is my personal opinion, but I think so.
Okay, so sorry for the interruption. Yeah, as Manish is saying, it's very correct. Like, according to the rules, like, we are not authorized to discuss directly the assignment questions that is coming to you, because that is the some integral part of your assessment to check, like, whether you are able to do or not. But yes, I'm making sure that we will solve the problems related to or similar to it whenever, whatever is asked in your assignments. So since I don't have control to what the type of questions will be asked, but yeah, please understand this fact that whatever the questions are coming, that is coming from the context or from the lectures part of the course only. So if we go through the lecture material, then we will understand that it's part of lecture material itself. Like, all the questions, I just saw the questions. All the questions were based on the condition number and some of the
Okay.
formulas.
I think we can start today's session.
Oh, okay, Lakshmi. Any issue, like Viveka?
No, ma'am. No, ma'am. Continue, ma'am.
Okay, thank you so much. So I'll start. So yes, in the previous classes, we saw what is LU decomposition and what is QR decomposition and why even we need this LU and QR. So basically, LU was a representation of a non-invertible matrix in the form of lower and upper triangular matrix. And why we did that? We did just to simplify our calculation. And in the end, we found that using LU decomposition without calculating explicitly the inverse of a matrix, you can directly calculate the solution of linear system of linear equation. So we saw that. And similarly, the same thing comes when you want to decompose in the form of orthogonal matrix and a upper triangular matrix. So why orthogonal matrix was of our prime importance? Because orthogonal matrix had this property of Q transpose Q is equals to Q transpose is equals to I. So this, which implies that Q transpose equals to Q inverse. Okay. So this property helps us in many ways. That's why one of the main reasons to change that thing into QR decomposition. And we saw that this QR decomposition is also called as Gram-Smith criteria, orthogonalization. Okay. So, last class, Billy had some doubt in LU decomposition. So, I will go to that LU decomposition again, like to solve how to solve that particular thing. But yeah, I understood every point of LU decomposition and what is that and how it came from. So, I'll make you understand the last. So, today we are going to the lecture 5 material. So, let's first complete the lecture 5 material concepts as quickly as possible. Then we will go to the questions, last year questions, and then we will solve the questions. Okay, so if you have,
Okay, ma'am. Thank you.
yeah, Millie, thank you. So if you have R2, that is R2 plane, and suppose U is a vector that is perpendicular to V. So V is a subspace. So what is subspace? That is closed under multiplication and scalar, the closed under scalar multiplication and vector addition. So we saw this in the first class. So I'm not repeating again what is subspace. So any line or any plane that is passing through origin, that will be a subspace of R2. So this is a line passing through origin. Now you have this subspace as let's say V. Suppose this U is a vector that is perpendicular to V. Now this information is giving to you. Now you have to find uh, so suppose what is this? U is perpendicular to V such that mod of U is equals to 1. So this is orthonormal set. Let's suppose this is these things are given. So since this is perpendicular, so this will the U transpose V is equals to 1 because that according to perpendicular criteria. So what is how it is this one? Because cos theta should be equals to 90 degree. Okay, that is the inner product of two vectors equals to 1. Similarly, these things we have assumed. Okay. So, so we have to observe T is a transformation which reflects every vector in Rn through V. So what is that? Suppose you have any vectors. These three vectors are there. Now this will act as a reflector. Now you have to reflect this particular vector over this particular plane. Suppose this is a vector V1. Then this vector should come such as V1. V1 star because this will reflect the particular vector over this plane V. So this U are all the perpendicular vectors. So you don't assume like in reflected all the vectors will reflect. The reflectors will only reflect the perpendicular vectors. Okay, so that's why we saw this U vector. Okay, so this is forming the orthogonal basis. So what we have to make sure first of all the vectors lying in V should be equals to V, isn't it? All the vectors lying transformation of U should be equals to minus U. These all the vectors who are perpendicular to this particular thing. Others all perpendicular vectors are U only. Okay, so that should comes as minus U. Okay, so this is our aim. Okay, a T is a transformation. Okay, so T is actually a reflector. So this is our aim. So every vector that is belongs to R power n can be uniquely represented as a linear combination of U and V because these are the orthonormal bases and we have assumed these things. These are the assumptions. Okay. These are the assumptions. So this X is nothing but alpha U plus beta V from the property of linear independence. Now what we want? We want this particular thing to happen. This is minus alpha U plus beta V. So as we know, every transformation can be represented as a terms of matrix because that is a linear transformation. Okay, so how will we see? We will see now. Okay, so to construct the matrix representation of T, Sir took a particular way. Sir took this UU transport. Let's see this particular vector, this particular matrix, how it looks like. So if you find this UU vector, okay, laptop is okay. UU vector. So let's see this. Let's name this UU vector as a projection matrix because it has some particular properties. You always remember what is projection matrix. Okay. Then if you multiply with U, then you are always getting U, and if you multiply with V, you are getting 0. This is the projection matrix property. So what is projection matrix? First of all, projection matrix follow this particular property. This p square is equals to p. Okay, so this property is there, and in this particular case, our p is nothing but u transpose. And what it is giving? It is giving this p of u is equals to u, whereas p of v is equals to 0. But what we want? We want some matrix T, A or T of V is equals to V, whereas T of U is equals to minus U. We want this, right? Some value we got from U, so we have to just reverse it. Now, how to reverse it? Let's name a vector, a matrix Q is equals to I minus 2UU transpose. Now, let's see this thing. Q of U is nothing but I minus UU transpose, multiplication of U is equals to U minus 2UU transpose into U. That is, you are getting as minus U. Whereas Q of V, you are getting this V minus 2UU transpose V. And if you associate it, so using associative property, what you are getting? V minus 2U, you can keep out, then U transpose V. So this we know as 1, this we know as 2, this is nothing but 1. Okay, yeah, V transpose U, and then U, and this is minus 1, and this is V. So this is what we want, right? So that's why this particular matrix is called reflector. I hope you understand what is reflector. So we have to understand properly what is reflector. Now, what you had a plane, that is a subspace passing through a line passing through a origin. That is V vector. Okay. Now you had a U. U is all the set of all the vectors that is perpendicular to V. So what is a reflector matrix representation is I minus 2UU transpose. This you please remember, okay? That is a matrix in the plane of R 2 cross 2, okay? Because U is having the length of 2, that's why this is U cross 2. Check whether this is orthogonal matrix or not. So then check whether it's orthogonal matrix or not, then you can check directly that it is the orthogonal matrix using this property. Now you have to find it what is this. So if you are having this particular thing, okay, R power n for fixed U belongs to R power n, define V, that is V, this is belong to V, that again if we can see this graphically, okay, such that this VU, the VU as all the vectors that is perpendicular things, this V is equals to 0, okay. So this is V is all the vectors are orthogonal to a fixed vector U. So easy to see that V is a subspace of Rn. Now reflection action. So reflection action is reflect through the subspace V. Okay, you're reflecting it with respect to subspace V or reflected. Now we have to see the rank of this matrix. That is very, very strange. Now see what is this rank. Tell me what is this rank. What is the rank of Q? What is the rank of Q? So since we have assumed it initially that U had a norm of 1, but if it is not written anywhere, then you have to divide this norm by mod of U square. So what is this? Q is nothing but I minus 2UU transpose divided by mod of U square, 2 norm square. Okay. So we can see this, if you see this UU transpose, so if we can see, if you multiply this U matrix with this one, this is suppose A, this is some B. So this is a multiplication of this thing, this is a multiplication of this particular row, this is multiplication of this particular row. So actually you all have a linearly dependent rows because all are multiplication of it. So this rank is nothing but rank is 1. So only you have one independent row, that is 1. So this is 1 and this is also 1. This because rank should be subtracted with the equal rank. So this particular matrix have rank equals to 1. So that is very strange. The reflected have rank equals to 1. Okay. I hope you can it's clear. So this is rank equals to 1 update. So this is all about reflector matrix, and that reflector matrix is nothing but it's a orthogonal matrix that is following this property. Okay, and in the last also we will see in this lecture only that we for the condition number to be equals to 1, that is a best possible
No,
thing.
madam.
Yeah, Manish.
Can you please tell once again that why the rank is 1
Okay,
of
okay, okay,
two matrix?
okay. So let's have some matrix. This is if you have any type problem with this thing, let's have example. Let's have example as 1, 2. Okay, and U transpose will be 1, 2.
2, 1, 1.
Yeah.
Yeah.
So U transpose will be 1, 2. This is 1, 2. So what is this? 1 cross 2. This is 2 cross 1.
Hmm.
You will get 1 cross 1, right?
Yes.
If in another case also, if you want to take this vector as 1, 2, because every time whenever we assume a vector, that vector should be column vector, not row vector, okay? So this is 1, 2, this is 1, 2, okay. So this is 2 cross 1, this is 1 cross 2. So what you are getting? 2 cross 2. So this one, this is 2, this is 2, this is 4. So you can identify the second row R2 is nothing but 2R1. So only one
Okay.
uh,
Yes.
independent row, okay? So that's why this is,
Yes.
okay, in every case, this is rank 1. This is very
But
strange.
Q is also rank 1.
Which one? Yeah, yeah, Q is also rank 1 then.
Q.
Yeah, yeah. Because that's I minus U transpose divided by mod of U square. This is 2 now. Because this is rank 1, you cannot subtract with a different rank matrix with a different rank matrix. Okay. So according to the property of addition and subtraction of the matrix, this Q is also rank 1 matrix.
Okay.
Yeah. I hope this is clear. So moving ahead, now let's simplify these things, okay? We have another question. Let x, y belongs to R power n such that mod of x is equals to mod of y. So these are, so whenever we go to the linear algebra, sometimes we have to assume with some initial beliefs. So these are the given things, okay? These are the given things. Mod of x is equals to mod of y. Then there exists a reflector q belongs to R this n cross n such that qx is equals to y. So how to observe this particular thing? So you have this x and y. Okay, this is mod of x and this is mod of y. Suppose two vectors are there. Okay, don't see like this. Later we will see through circle thing. But yeah, you have these two vectors such that is mod of x is equals to mod of y. This is norm of two vectors are same. Then there exists a reflector, these things. You have to identify what is q. You have to find this q, okay? So we have to observe this x plus y and x minus y. Let's say, if you find this inner product, what is the inner product? So if you calculate the inner product when mod of x is equals to mod of y, then this particular thing is 0, because if you calculate split it out, x transpose x minus x transpose y plus y transpose x minus y transpose y. So we know the inner product can be written commutatively. So this is cancelled. This is this mod of x square minus mod of y square. This is equal as we have assumed. Then this is 0. So what does this mean? This means that suppose you have x vector, you have y vector, then what is the sum of these vectors? According to triangle law, this will be sum of x vector plus y vector, okay? And if you find x minus y vector, so this is minus y vector. So according to law of triangular, what is x minus y vector? This will be something around x vector minus y vector, okay? Since the inner product of these two things are 0, then this means that x plus y and x minus y, when mod of x is equals to mod of y, then it will be orthogonal. Okay, and remember in our
How
reflector
did
case
we
also,
get
yeah.
how did how did we get that x plus y transpose dot product x minus y is equal to 0? How did those terms cancel out?
Okay,
Minus x transpose.
yeah. So this inner product, x y is equals to yx. This is nothing but x transpose y is equals to y transpose x, right? This is,
Yes.
if you split it out, this is what? x1 y1 plus x2 y2, so on xn yn, right? And this is also
Okay.
what? y1 x1 plus y2 x2, so on yn xn.
Okay. Okay.
Yeah, this is equal, right? So this will be cancelled. So the inner
Okay.
product property also states that these are commutative in property. So this is what orthogonal. Now try to relate that whatever we studied just 5 minutes before. We studied, like, if we have the plane of V and if we have the perpendicular set of vectors, then we saw that the reflection was what? Perpendicular set of vectors, what? U was. In our case, U was that. So the Q was nothing but I minus U transpose divided by, sorry, I minus 2 U transpose divided by mod of U square. Okay. If it is the orthonormal vector, then mod of U will be 1 only. Okay. So now think in our case, this is also we are trying to find such a way. Now we found two set of orthogonal vectors. Okay. Now we have to find such that this qx is equals to y. So qx is equals to y. What does this mean? That here, but rank is 2. Reflection about y-axis is, can you express reflector matrix is rank 1? Yeah, reflector matrix is rank 1. Wait, I'll give you one examples. Wait, you are giving one, give me one example. For example, the reflection about y-axis. Y-axis, okay. This is 1, 0, 0, minus 1. Is it orthogonal? Can you check that? The basic thing that we can see, okay, this UU transpose thing is ortho, this rank 1. Okay, let's keep this for hold. I'll explain how that thing is rank 1. Uh, we will see with example also. That is rank 1 only, because this UU transpose divided by mod of U square is rank 1. So you cannot subtract with a different rank matrix. Okay, if a different rank is there, can you able to subtract it? I think no. Let's see with this example only, x plus y, x minus y. We will verify it. I is rank 2. Okay, I is rank 2, that's I agree. But can you subtract with I minus? If it is I minus 2, 2 into 1. Suppose this is rank 1. Suppose 1, 2, 2, 1. Okay, okay, okay. So sorry. That's my mistake. Okay. Okay, we saw this particular thing as, okay, okay, oh, so sorry. We saw this particular thing. This is rank 1. Okay. Then Q is equals to, suppose you will have 1, 0, 0, 1, and this is, let's see this example only. This is multiplied by 2, okay? 2, 1, 2, 2, 4, then 1, 0, 0, 1 minus 2, 4, 4, 8, because that will be same. Okay, so this is minus 1, minus 4. This is minus 4, minus, minus 7. Okay, so in this case also, this is not rank 1, but sir taught somewhere that is reflection is a rank 1. So this is okay. So my mistake. As thank you. Solve one in the one example in Q reflector matrix. Yeah, we will solve. We will solve. Anyway, we are coming to it. We will see the exact example also in the class. Also, such hot. So basically, what we saw here, if Q transpose is rank 1 also, we are not getting, we are not sure that this one is also rank 1. Okay, where this rank 1 was written, let's see this thing. This is what written, rank -1 or rank 1 update of identity. Okay, sir never taught about this thing that Q is a rank 1, but rather he was telling that why U transpose is a rank 1 matrix. So yeah, this is not sure that Q will be rank 1, my mistake. And if it is Q is rank 1, then we are not able to, we will not be able to translate the reflection of a any vector through any plane. That is also my mistake. So yeah, we will see some examples. Okay. So till now we saw up to this point, this q x minus y uh, is orthogonal to x plus y. Okay. Now, as we remember, what was our aim in case of QR decomposition? We were trying to make this particular thing as a 0. Why 0? Because we were having this ax is equals to b, suppose. Then we are trying to make this, whatever this matrix is there. Suppose this matrix is A, B, C, D, E, F, G, H, this particular matrix was there, then what we're trying to assume this we are first making this particular thing as a 0. So we are multiplying this particular thing as q inverse of x so that this thing will become 0. So that we will have some values in this q matrix. We will have 0. Then later we are making it this particular thing as 0, this particular thing as 0, then this thing, this thing, this thing. So what was our aim in that case was to make it this thing, A, B, C, D, suppose, E, F, G, H, and this is as a 0, 0, this is 0. So that at the end you will have Q, X, this is Q, X, Q inverse of X is equals to U. This is was the upper triangular matrix, okay. So that, this is A, sorry. So A will be Q transpose, this is Q, U. U was nothing but R. Okay. Our aim was that, if you remember in the previous class, so we are trying to make this particular thing as a tau and then we are making it 0. Let's see this physically also. So suppose you have this V vector as this particular thing. V belongs to R power n such that U or V will be 0 for some fixed Rn. Let's assume the similar plane subspace passing through origin. So this was the hyperplane that is in R power n passing through origin. Okay, in that case, our reflector was this thing. Okay, now let's say x and y be a vectors in R power n. Mod of x and mod of y will be this thing. Then we saw this x plus y is perpendicular to x minus y. This means this thing. So any vector, given any vector x y, such that this particular thing is holding, there exists a reflector such that qx is equals to y that we saw in the previous problem. So we are yet to solve this problem. Now, since x minus y is orthogonal to x plus y, so this q is nothing but replacing x minus y, u by x minus y. Okay, you are replacing u by x minus y. So if you solve this, q is equals to I minus 2 mod of u square x minus y in multiplication with x minus y transpose. Then after solving, qx is equals to y you are getting. So Q is nothing but this particular matrix. If you solve this particular matrix further, let's see. First of all, if we wanted to identify these things because that was our condition such that Qx is equals to y. Now, if you solve this particular matrix further, so how it is written. Okay. So I hope this is clear. Qx is equals to y, height is there. So you have to firstly check with some values also. So if you want to check, let's see some this thing. I minus divide 2 divided by mod of x minus y square. This is x minus y multiplication by x minus y transpose, and then you are multiplying with x. So you can write this x vector as mod the 1 by 2 x plus y plus 1 by 2 x minus y. So if you solve this further, you are getting this as y. You can solve it further. That is not an issue. So let's see one of the example is how it is causing this particular thing as an action. This particular thing as an action. So what is the aim of reflector? Let's see that. Okay. Till now we saw what are the reflectors and what is the rank of the reflector, how the reflector works, with what is the formula of reflector, and what is the case when we have x and y vector such that qx is equals to y, then also mod of x is equals to mod of y. So we in that case we found this reflector matrix as q as written here. Okay. Now let's say take any vector x belongs to R bar n. X is nothing but x1, x2, xn, and y is nothing but, let's say, minus tau 0, 0, 0. Okay. So what it is here, tau, in order to make it mod of x is equals to mod of y, you have to make sure this tau should be equals to mod of x1 square plus x2 square plus xn square. I hope this is clear. This is mod of x. So this is tau. Tau is nothing but mod of y is nothing but tau. Okay. So tau is nothing but these things. This is equals to mod of x. Now, we have to see the reflector. This reflector is nothing but this thing. So if you find this particular thing, the denominator, this is nothing but 2 tau x1 plus tau. So and then you choosing this reflector, what it is giving, q of any vector, that is any vector x1, x2, xn, you are getting this particular operation. This is minus tau 0, 0, 0, 0. Okay. Now, this is a one column of any matrix. Okay. If you assume this is as a one column of any vector, you are getting this particular desired output as an output. Because in case of QR decomposition, we were doing that thing. Okay. So this is a one way to do that using reflectors. So this is one of the use of reflector. First use was to reflect everything over a subspace. Second use was to check every vector in a matrix. Now let's see how it can be done. Okay, so if we see this A belongs to n cross n, be an invertible matrix, then this is the A matrix. So we have to construct Q belongs to n cross n, a reflector. Then what should be the Q1 of A? So you wanted that Q1 of A should be, this is 0, and this some matrix will be there. This is A1 transpose. What I'm trying to do, I'm converting this particular thing to this particular thing using this operation, using this operation, using this operation. So if you convert that thing, that will give you some matrix of Q1 of A. Later, you want to convert this particular matrix to this things. Okay, you want again some different value to be these things. Then again you will multiply with Q2 of A. And this will goes on, and finally you will get what will get? A1 of transpose, A2 of transpose, A3 of transpose. This is A4, 4 of transpose. Sorry, star. You will get 0, 0, 0, 0, 0, 0, 0, this 0, this thing you will get. Any vectors, values you will have.
Ma'am,
Yeah.
ma'am, actually it is similar to LU decomposition.
Yeah, it is similar to value decomposition.
Yes, okay.
Yeah, that's very true. So, but in case of QR decomposition, I'm making sure that this particular thing that you're multiplying is an orthogonal matrix. It's not a normal lower triangular matrix. In case of a normal lower triangular matrix, we saw that is a lower triangular matrix. That was having the predefined value. At suppose L21. L21 plus value is having, this is minus of A21 divided by A22. Okay. This was the value of L21. Then L31. This was the value of minus 31 divided by A33. We are making sure these things. Okay. But here in case of these things, we are multiplying with a orthogonal matrix. Okay, so that is a base motivation, like why we are studying this. That was one of the example. Okay, now if you want to solve this ax is equals to b, that is a difficult problem. Suppose you have n cross n matrix, that you cannot solve this inverse of A matrix. In that case, you will rather convert that A matrix to a QR decomposition. Then this particular thing that you can write Rx is equals to Q transpose B, and Q transpose B is nothing but Q inverse. Transpose in case of orthogonal representation, Q inverse equals to Q transpose. That is very easy. And then R is upper triangular matrix. So using a simple mathematics of backward substitution, you can solve this uh, system of linear equation. Whereas in case of n cross n matrix, the computation required for calculating the inverse of a matrix was truly very high. That's why we guys are doing like this. We are converting it to either LU or QR. QR is very famous because QR is like Q transpose is nothing but Q inverse. So just calculating the transpose, you'll get this thing. Okay, so this was the ambition. Okay, so this is the process that we followed. First, we are multiplying this Q1 A, that we are getting this is, then Q2 of A, then we are getting this. This is particularly R, and this is Q. So R A X is equals to QB. This Q transpose. So Q transpose is also a orthogonal matrix. So one property I'm telling, lower triangular matrix inverse is also lower triangular. Similarly goes for orthogonal. That's why we are converting into QR and LU. Okay, so this was the main thing. And then sir trying to make you understand like what is a computation required here. For example, let's see this thing. Q1 of A, you're multiplying with Q1 of A, then Q2 of A, Q3 of A, focusing each column one by one, okay, as we saw here, focusing each column. Then what is the computation required? So let's say you're multiplying first Q1 of A, that is nothing but I minus this. Let's say this is some scaling factor, this gamma UU transpose A, because that scaling factor will be different, not necessarily this Q2. Most of the time it will be Q. We can represent this Q also, this gamma. This is nothing but 2 divided by mod of x minus y square. This U is x minus y. Because in our case, mod of x is equals to mod of y. So this should follow. Okay. So the computation required is total of order of 4 of n square. Whereas in case of this thing, total flop is 2 order of 2 of n cube. Okay. Whereas in case of inverse, what will be the flops required? Tell me. We saw what are the number of multiplication and additions required in one of the week. I don't remember. That is if we have A, M, N, and Q, suppose B is.
Order of n squared?
Yeah, I don't think that is log of n square. You'll have more. Suppose this is P, then the number of multiplications required is M and P. So it is more than this thing. And additions also you'll have, I think that is, this is number of multiplications. Additions I don't remember, but I think Guru Swami, if you remember, we had that expression. This is something sum plus sum. Okay, so
Ma'am, I have doubt on
yeah.
that flops is there, ma'am, in computational complexity. Where we use this flops,
So
like how we use.
okay, flop. What do you mean by flop? First of all, flop is a number of additions, like computation required for the number of additions and multiplication. Okay, so sir is just trying to
Flops
identify,
are
like if
floating point operation.
overall, if you're trying to calculate the QR decomposition. Yeah, Lakshmi, tell me.
Now, I was just telling him that flops stands for floating point operations. In a computer, how many operations it takes to compute,
Uh,
do a particular computation.
yeah, that is true. That is a actual definition of it. But if you want to identify uh, what is a computation complexity, then you'll calculate, like if you were there in the first or second class, we calculated the flops required for inner product. Okay, so if you remember the inner product flops, so that flops was order of 2n. Okay, so for every row we are calculating order of 2n. Then you have the n columns, so we are calculating for n columns, that is the order of mn. Okay, so m is the number of rows and the n is the order of the number of columns. Okay, sorry, number of rows. So number of elements that is there in the rows. So that is the number of lobs. So we calculated, suppose x of y. So this is x1 y1 plus x2 y2. This is x and yn. So number of addition is nothing. What is the number of additions? This is n minus 1. Okay. Number of multiplication is m. Sorry, n. So total number of computation requires is n minus 1 in one inner product. But in matrix multiplication, you are recursively doing it for many columns. So that's why if you calculate the inverse of a matrix, that is only a matrix multiplication. And if you calculate the inverse of a matrix, that is what is the inverse of matrix formula? That is adjoint of A divided by mod of A. So this is cofactor calculation of A, cofactor of A transpose, sorry, this is mod of A. Determinant, let it keep it constant. Then if you calculate this cofactor of A, then you have to calculate this minor of every row. So that is a very complex thing if you calculate it for more thing. But even if the flops are here, but the computations are easy here. So that's why we are converting this this particular thing to QR decomposition and LU decomposition. I hope this is clear. So again, sir is telling how many flops are required, because we are anyways we are multiplying it with respect to for n minus 1 reflectors. Okay, so for if one reflector, it is this one reflector, it is how much? N square. So if 4n square plus 4n minus 1 square, okay, you can see this, but the later we are getting as 8n cubed by 3 flops. And finally, by back substitution, this is the number of flops. So you just see how one reflector is causing. So and then you are multiplying with n minus 1 reflector. So if you multiply with n minus 1 reflector, this is the number of flops. And if you sum it, then the total number of flops required for calculating QR decomposition system of linear equation. Okay, so till now, let's summarize this. This is very important. We have saw two decomposition of A. First one is LU and QR. So one thing to note is, what is one thing to note? These two decomposition were only applicable for when A is invertible matrix. Okay, when we are trying to calculate A as the inverse of A, that is an invertible matrix. But invertible matrix means what? The determinant should not be equals to 0. Isn't it? So whenever you do LU decomposition, the decomposition is unique in nature, and whenever you do QR decomposition is also unique in nature. And this particular thing, QR decomposition, one can also see through the graph space orthonormalization. That is the only step-by-step procedure, finding the basis, orthonormal basis of any matrix. If you want, we will see this particular thing. Some of the classes. This is graph space criteria. So basically, what you do in the graph space criteria, I will tell you. Can just refer the Wikipedia, or else if you want to see, you can see now only. If you have the vectors v1, v2, this is vn vector, and these are set of some.
Ma'am,
Yeah.
ma'am, one doubt.
Yeah.
That is LU decomposition of a matrix unique? According to what I learned from some other YouTube channel, it's that there are two methods. One is Kraut's method and the second is Doolittle's method. So LU decomposition can be several. It's not that for a matrix, LU decomposition is unique. But am I wrong? Is it that always?
I think it is unique, Lakshmi, because if you saw this LU decomposition, so we'll see. Let's wait for a while. You can see this L.
Because in certain cases, first they find U and then they find L.
Yeah.
And
But
then
in that case also it will be unique. Why I'm
in
telling you
that
that
case,
reason? Because
no, they consider L to assume L to be a matrix that diagonals all ones. And
yes, that's true. That's true.
the other case they start with U and there they assume U to have diagonals all ones. So in that case, it can't be unique, right? LU decomposition,
Okay.
many LU decomposition.
Okay, but at the end, what we are trying to find is this value is perfectly equal to this particular thing. Have you ever wondered this L21, the value is you are getting always A21 divided by mod of A22. Is this true for you also in both the cases? In either
I am
way,
not sure about that. Yeah.
yeah, in either way, I checked that because I also had this issue, but downward. So in either cases, whatever you are doing, the values are fixed. This particular thing only we are getting this A. Suppose A is a matrix, so this is A11, A12, A21, A22. So if you want to rectify this particular value, so the L21 that you are getting is A21 minus A21 divided by A22. This is the value that you are getting. Similarly, L31, the L31 you are getting as minus A31 divided by A11. So sorry. This is A22 or A11? A22 or sorry, A22. Let's see this. The values we are getting for sure, that is uh, fixed values only. Okay, so this thing should satisfy. Let's see from here only. So what is our aim? Our aim is to convert this A into LU decomposition. LU is nothing but LU, and finally we will solve using forward substitution. So if you have this L21 in assignment question 5, LU is unique. They have given LU is unique, but the answer key they have given is wrong. Yeah, Guruswami, in that case, you just raise a ticket or raise a voice against it. You just mail it to NPTEL team. They will rectify it. Don't worry. Assignment 4 question 5. Okay, I will make a note of it. I can also pitch. Assignment 4 question 5. So according to you, LU is unique or not? Tell me. Okay, but as far as I know, LU is unique only. Uh, I have still doubt. Okay. So anyway, whatever way you are following, uh, the thing is you are getting this particular values as a constant values as these things. A21 divided by A11. This L31. If you find this L31, the L31 is minus A31 divided by A11. So whatever A vector matrix will having, you will have these three values. Then if you multiply with similarly Ln1, so same similar goes for Ln1. Okay. So Ln1, what will the value of Ln1? Ln1, this is nothing but minus of an1 divided by a11. Okay, and then you will calculate this L32. So L32 will be, this 2 will be there, okay? So L32 will be minus A32 divided by A22. These values is same. You cannot change that thing, okay? And based on this LU, you are trying to find this U. Okay, so U is nothing but this A L inverse of A. Okay, so later what is, let's see this later what we are trying to find it. So this particular thing is column 1, column 2, and continuing this we are calculating L of inverse. Okay, this is this L21. So what we are trying to do, this whole multiplication, L21, then L31, then so on, Ln1, then L32, then this always goes to N2, and all up to this till the point that we get the upper triangular matrix and the uh, the upper triangular matrix, and you will have this the particular multiplication. This particular multiplication is nothing but L inverse. Okay, So this particular multiplication is that L inverse. So this L inverse is unique, as far as I know. Now, if you convert this, this is L inverse. This now the you will get is based on this particular thing. Okay. Ambili, sorry. Ambili, are you getting this point? You were having the doubt in this LU decomposition, why we are doing this and how we are doing. Are you getting that point?
No, ma'am.
You are not getting? Okay, let's see. Let's go one by one. Okay. So basically what we are trying to do, we are changing or we are modifying the one particular value of any matrix. So basically you have Ax is equals to B. Okay. Ax is equals to B. And now you're converting A as A is equals to LU. Okay. Now, if you're multiplying particularly L21 with A such that these all are identity matrix. This is identity matrix. This is identity matrix. Such only modified content is this one. So what should be the value of this one? So your aim is you should get this thing as 0. Rest any other value, don't care. This thing as 0. So if you multiply L21, this is L21, A11, this is A11, L21, A11, this is 7, right? Okay. Row with column. Okay, you see this properly. This L21 multiplication with A11 plus A22 is equal to 0. You want this. You want this. Okay. So what should be the value of L21? L21 is nothing but minus A21 divided by A11. Rest all will be same as identity matrix. So you are getting this particular 0 using this L21. Now, you want to make this particular value 0 by multiplying a matrix that is L31. Okay. This is what? L31. Similarly, if you calculate the L31 value, the L31 is nothing but minus A31 divided by A11. Okay. This content will be modified, this L31 content. Okay. And in this way, you will get L31. Now, L41, because you have to make this particular thing as 0, then this particular thing as 0, because you want to make this as this particular thing. Okay? This will have values, this will have 0. This is upper triangular matrix. Why we want to make this thing as 0? Because we are making it 6 things as an upper triangular matrix. Rest others all 0. So that's why you multiply with this all the L matrix such that you'll have a U matrix at the end. Okay. So what should be the values of L matrix? That I'm telling. Okay. And these L, all the multiplication of L that we are doing it till now is L inverse. Okay. Now, this is L inverse. Okay. So what should be the value of L? Okay, this is L inverse. You have to inverse it and you have to find it. So, I hope this is clear to this point. Did you get some point? What is LU?
Ma'am, actually, what is L21? How we can represent the matrix
L21.
Only one element. That is a confusion.
Okay.
Actually, other points are clear, but how to represent?
Okay, L21. Okay. Let's see. This is the identity matrix. This is identity matrix, okay? This is 0, 0, 0. If you multiply this particular thing with first row, for second row, first column, what you will get? Don't you get this thing? Others all the as 0? Because this is 0 only. Identity what? 1, 1, 1, 1, 0, 0, 0, 0. Right? These things are values, right? So if you get this, multiply this L21 plus A11 plus A21. This is A21. And you want to make it as 0. Okay. This is A31. So you choosing this particular value of L21 will make this A22 0. Rest all the values of this L matrix is identity value. Same as identity value.
Okay, ma'am. Okay, clear.
Yeah. This is very important to understand because you may expect like 1 or 2 questions from LU decomposition and QR decomposition. So if the L matrix is R, then how will you calculate? You just have to calculate, replace with L21 as minus of A21 divided by A11, L31 as minus of A31 divided by A11. Similarly, and now at the end, what we found, that is also very strange. This is Q came. Okay, wait. Okay, this was my ambition. Aim. Now what we found, the L inverse matrix that you are trying to get, the L inverse matrix that you are finding, this is nothing but this particular thing. So L is nothing but you are getting this L matrix is nothing but this particular thing. This is 0, 0, 0, 0, 0. Okay. You are getting 1 upon minus L21 minus L31. So whenever that question comes, you just have to, you remember this thing and you try to find this L21 based on the A matrix, L31 divided by A matrix, and you observe that question will be solved. LU decomposition solved. Once you find this L, so A is equals to LU. So what is U? U is nothing but L inverse A. Okay. And when you try to calculate L inverse also, this minus will be simply replaced by plus. And rest all same. Because lower triangular inverse is also lower triangular. Okay. So I hope you don't have any problem in any LU decomposition. So whenever the L is asked, so L is this thing, and these particular values we saw, what should be the values of these things. Now, whenever U is asked, you can directly calculate L inverse A. I hope this is clear. If you want to understand how this L inverse is directly the minus things, so in this way we are writing L inverse. First of all, we are just making it E transpose. E is nothing but identity. Suppose E2 is there, then 0, 1, 0, 0 is there. E3 is there, then 0, 0, 1, 0. Based on the N matrix, you can check this. And finally, this L21 inverse L21 multiplication L21, this is I. So this is the aim thing that you just copy it. You can take a screenshot how to calculate LU decomposition, and based on this thing, you will not have any problem in solving the problem related to LU decomposition. If you have, we will discuss in the next class. But let's go to like week 5 only. Okay, so okay, so till this point we found this. Okay, up to this thing, I think this is clear. Now coming to the most interesting part of the course, that is the norm of a matrix. So till this point, that was something like somewhat it is doubtful, confusing or something. After this point, you'll never have the confusion once you understand the concept behind it. So what is a norm of a matrix? What do you identify the norm? So whenever we define norm, so norm can be defined in two ways. Okay, it can be either defined in the function of matrix, or it can be defined in the as only this norm. Okay, so norm can be defined as a function that is following this particular property, having this particular matrix A, because we know that any linear transformation function can be represented as a matrix. We saw in the like week 2 or week 3. Okay, similar goes for here. Let's say A is a transformation matrix coming from R power n to R power n. Okay, that is a linear function. So what is a linear function? Suppose you have x vector in R power n. It is transforming to A of x. This is actually a mistake. It should be R. Because at the end, if you multiply the norm, let's see, it depends actually. Depends. But we will see they will have various function R power n to R also, R power n to R square also. Because norm of a matrix is giving you the single value. It varies, okay? Anyway, the single value should also belongs to R. It is not a vector. If it is not a vector, then it should belongs to R. Okay. We will see there are some typos. Okay, here it is covered. Okay, this is R only. Okay. So a function that is defined from R n cross n, that is a matrix, to Rn is a norm if it follows this particular things. And the function is a R power n to R power n. Okay. So mod of A should be 0 greater than equal to 0, and the norm of A is equal to 0 if and only if this is equals to 0. The second property is alpha A, norm of alpha A is equals to mod of alpha into norm of A, such that for all A belongs to this particular thing and this thing. Okay, these particular properties, we should follow this. So norm of A plus B should be less than equals to norm of A plus norm of B. So we saw this. We saw this triangle inequality. So what is extra thing here in norm? The extra thing in here is sum multiplicative property. What is the sum multiplicative property? This particular thing. Norm of AB. Here AB is nothing but what is that? It is matrix. Okay. Should be less than or equals to norm of A multiplication with norm of B. Okay. Now first of all we will see Frobenius norm. Okay. So what is Frobenius norm? So if you append every vector of a matrix one by one making it down, so you can see this is giving you one long vector, so that we can represent that vector of A, that is A is a matrix. So this, if you sum it and square it, that is giving you a Frobenius norm. So what is that? This is nothing but A1 1 square plus A2 1 square plus all the values of A. This is giving you sum of all values of matrix A. Okay, square of matrix A. That is giving you Frobenius norm. Similarly, you can write it here because it is having n column, m rows. So you can write this, or similarly you can write this 2 norm of vector of A. Okay, I hope this is clear up to this point. To verify sum multiplicative property of Frobenius norm, you can say you can C, suppose C is A into B. So let's see what is the Frobenius norm of C or B. What is our aim? We have to identify this AB. Frobenius norm should be less than or equals to Frobenius norm of A, Frobenius norm of B. Because that's some multiplicative property you can identify using Cauchy-Squarce inequality. What is Cauchy-Squarce inequality? The inner product of any vector square should be less than or equals to their individual inner product. That you make sure it is following. Okay. So this was the Cauchy-Squarce inequality. So at the end, what we found, this is following this sum multiplicative property. Now let's assume take A as a linear function of r power n to r power n. Okay. So what is induced norm? So induced norm is defined as max of x not equal to 0 mod of x ax norm 2 divided by norm 2x. So basically this ax is also called range or image of x, that we are transforming from any x vector to any ax. Okay, this particular transformation is A, because A is nothing but a function only. Okay, defined from r power n to r power n. Okay, so this is magnification. So induced norm is nothing but max of x not equal to 0, this ax divided by x. Okay, so it is also a matrix norm. So basically whenever we see this particular property, so it is called as matrix norm. Okay, this is called as matrix norm. So whenever we see any norm, suppose 2 norm, 3 norm, infinity norm, every norm, that will, if it follows this particular 4 properties, then it is also, we tell that it's also indeed a matrix norm. Okay, so that we saw Frobenius norm is a part of matrix norm. So if we say Frobenius norm is a matrix norm, then definitely all the norms are also this matrix norm. So now we are saying that whether the induced norm is a matrix or norm or not. So we are verifying it. First property. What is it? This. So Have you ever wondered, whenever we write a function, have you ever tried to see what the physical significance of these things is meaning? So what we're trying to find, if you have this x vector, okay, and you're just multiplying with the ax vector, okay, now you're maximizing it, okay. So what you're maximizing, you're trying to find the value of a such that it is giving the maximum range. Okay. So you're trying to find the range of A such that the image is the length of the image is maximum. Okay, because AS is image. Okay, so if you try to find this properties, then what we are seeing it is following the property. All the properties are followed. So you just verify with yourself. So whenever this type of questions comes, you just verify with yourself so that you also know. Okay, what is this triangular inequality also? You just verify with yourself. Okay. Some multiplicative property is very, very important. That is new in other than vector addition and closure vector addition and scalar multiplication. Okay. So now moving to the next norm. So if you type norm of P, that is induced norm P, then you can write like this. That is also indeed a matrix norm. You can verify by yourself. So here we saw this is 2 norm. Okay. Similarly, you can write for the different norms. So if it is verifying for 2 norms, then it will also verify for other norms. Okay. Max of x not equal to 0, ax is divided by this thing. So in this things, what we saw, the matrix norm has this particular property. This is some multiplicative property. Okay. View matrix as a vector in Rn square, which is Frobenius norm. View matrix as a linear function from R power n to R power n, that is induced norm. Okay. So whenever we see matrix as a linear function from R power n to R power n, then that will be induced norm. You can verify that for every norm. And if you verify a matrix as a vector in R power n, n square, how n square? Because that was one vector, vector. This is also having one length. This is having one length, one length. So n length multiplied by n. So n square, right? That is having the length of n square, R power n square. Okay, this is also matrix norm, and also all the induced norm that we saw. What was the induced norm? Max of x mod of x not equal to 0. Sorry, max of ax norm of any norm, p norm. Suppose this is x. This is p norm. We are trying to find the range. Okay, I hope this is clear up to this point. Okay, so moving ahead. We will see that condition number, that is very, very important, and I'm sure that in the next 10 minutes, if we see that what is condition number or what is the property of condition number, we will be able to solve 80% of the problems of uh, week 5. I think Viveka left, but yeah. So if you calculate this matrix vector multiplication, now we are trying to observe if you have some permutation, perturbed values in A or any vector, then what will happen to the matrix vector multiplication? So give me some 2 minutes. I'll have a water and then I can come back. So hi all, thank you for waiting for 5 minutes. I just had water. So till now we saw norms, induced norms, and matrix norms. Now we will see some. We are coming to the condition number property. Now, if you want to see, let's have some a vector that is having some perturbed value. Then that suppose z, if a vector a is perturbed to this particular value, then you have to identify, let's see, the value that is multiplying with p a plus delta a, then the z is also perturbed by this particular delta z. So have you ever wondered this delta z will also be perturbed by the same quantity as delta a? What do you think? Like, the question is also here, given delta a is small, can we say that delta z is also small? This is what actually the sensitivity means. So what happens whenever, let's see some simple example. You have a matrix, the matrix that is A, okay, and you're multiplying with X, okay. So this A is a matrix. So what you're trying to do, A11, A12, A12, A21, A22, okay. This is, let's see, this is X1, this is X2, okay. So this is this one, okay. What you're getting, A11 X1 plus A12 X2, A21 X1 plus A22 X2. Okay. Do you think that if we multiply, if you change x1, x2 values by delta x value, the same quantity will be reflected in A? I think no. So in LU decomposition and QR decomposition, what we have seen, you are multiplying for every row, every column. You are multiplying with a different matrix. That is L31, L21, L32. Okay, these values. Okay, so what it is? If it is accumulating in a order of n. Okay, so we need to make sure this accumulation of the error should be within a converge analysis or converge number. Okay, so this is what the condition numbers comes into the picture. Okay, that is very straightforward. And why we guys are very much focused about orthogonal matrix, because that condition, their condition number is 1. That is the minimum thing. Okay, the condition number is 1 means that the same quantity will be reflected in vector matrix multiplication as the same quantity is reflected in A or any vector. Okay, let's see this. The similar thing is there, Q21. You are checking this, everything is perturbed. Okay. Now, if we see this particular thing, let's see P is equal to this thing. If it is an invertible matrix, in this case, I think these two things are different. Okay. So if you see A as 1, 1, 1, and you are multiplying with P of A, then you are getting this delta A as 0.001 and 0.001 delta A, okay, and delta Z also 0.001. But if in the second example, if you see delta A with the different values, then you are getting different values, 0, 2. That is very different, okay. This is the whole values modified. 0.001 is fine, but if it just changes with 0, 2, that is whole things are different. So that's why sensitivity analysis is important in the perspective of vector calculus as well as AIML applications. Because if at any point you are trying to find the neural network weights, and if it is perturbed with some value, then what should be the range of perturbed value or the perturbed matrix, so that it won't affect up to a certain extent. Okay, and that's why the perturbation is carried on the orthogonal matrix. Okay, that because their sensitivity is zero, is the minimalist. Okay, minimalist. Now, let's example PA is equals to Z. If we multiply P into A plus delta A is equals to Z plus delta Z, the sensitivity analysis result shows this. Delta Z mod of Z should be less than or equals to mod of P. This is norm of, okay, this P is a matrix. And you are multiplying this particular thing here, P with the A. So this is the actual sensitivity. You please remember this thing. And this is also called condition number. Okay. So how this results come into the picture? So this is the proof. If you go sim, this is very, very simple. But if again I just want to solve some problems also. Let's see, just go very fast. P of A plus if you multiply this thing, and if you represent this as z plus delta z, then P of A plus P into del of A is equal to z plus delta z, and P of delta A. So if you just make it 0, then P of delta A is nothing but this things. Okay. Similarly, this delta z is nothing but P of delta I. Same thing. And if you take the norm, both sides. Okay. So this is norm mod of delta z, let's say equals to how it is. How it is, tell me. It is through Cauchy-Schwarz inequality. This is through Cauchy-Schwarz inequality.
Madam, it is because of subdivision, submultiplicative property, no?
Okay. So sorry. Yeah. Thank you for correcting. Thank you. So yeah, I forgot it. So this is okay. And in fact, the submultiplicative property also comes from Cauchy-Schwarz inequality. So mod of AB is less than or equals to mod of A, mod of B. Again, this proof is given by Cauchy-Schwarz. Okay, so that's why I was getting confused. But yeah, you can directly use this submultiplicative property as corrected. Okay, so this is giving these things, and similarly this is giving these things. And if you just represent it, you will get this particular thing. You please go through it. Okay. So again, I'm repeating. My aim is to get some familiarity with the concepts of the particular week, as well as we will solve some problems. So as due to time constraint, we cannot go through every small things. But if you have any doubt, you just stop me any point. We will again go through that. Okay. So coming to the condition number. The condition number of a matrix A, let A is R n cross n be a square invertible matrix. So here the condition is square invertible matrix. Then the condition number of A denoted as K2 of A is defined as this particular thing. Now the upcoming lecture is only based on the property of these things. Okay. So this is very, very different thing. Like it has certain properties. What are the properties? Let's see. As we know, this I is equals to A of A inverse. We can write, right? So if you just make it as norm, then you can, using some multiplicative property, the K2 of A is greater than or equals to 1. So minimum value of K2 of A is 1. Okay. Now, okay. So the best possible value for condition number is 1. Okay. So we need to make sure we need to keep the take the P the matrix such that the condition number is 1. So in all the orthogonal matrix, but I'm repeating this again and again, but still, matrices, this includes reflectors, this includes rotators, okay, as Q, it follows Q transpose Q is equals to Q transpose is equals to Y. Their condition number is 1. Okay. Same thing is there. If Q belongs to n cross n, orthogonal matrix, then I is this thing. Then condition number is 1. How the condition is number 1? This is Q. This is mod of Q. This is mod of minus 1a. Okay. This is minus 1a. Okay. This is 2. So this is nothing but 1 upon this is 1. Because Q transpose equals to Q inverse. Okay. So that's why sensitivity result, concept of condition number. This is the, and now we have come to the last lecture. Okay. So operation we saw, this is a matrix vector multiplication. Assume P is a square invertible matrix. Okay. Now we saw this is the property that should follows. And we proved also this is a range of K2 of P. So the best possible value also we saw, this is one, that is case of that is really in case of orthogonal matrix. Okay. So also condition number, if we saw some, these are some analysis over these things, and like we saw induced norm. This is also induced norm, right? That we saw, that we can also write as a max of magnification of A, as was I was telling, that you are making it as A of X and then trying to find what is the range of or the length of the A of X. Okay, so this is also can be write as the max of magnification of A. Similarly, minimum of magnification of A can write as this particular thing. Okay, so we found it. And we know that K2 of A is nothing but A inverse of 2. Okay. Now, this A inverse, if you just take this max of magnitude of A, then you can write this max of magnitude of A. And this A inverse you can write is 1 upon min of magnitude of A. Okay. Just making it max because you know that the induced norm is what? Induced norm is nothing but max of x not equal to 0, a of x divided by mod of x. That is 2 norm. Okay. Similar thing is goes here. Uh, Actually, we are not left with much time, but yeah, this is nothing but you are trying to trying to write max and min in opposite form, and how you can write this is nothing but that thing only. Simple thing. This is very straightforward. The same thing goes for min thing. But if you want to write this particular thing, then it should be greater than 0. And you can write this max magnitude of A minus A is nothing but 1 upon min of magnitude of A. So that is a proof. How it is this thing? Uh, I think if it is not, if you don't know, I'll tell you again. But if A is a vector, is a matrix from R power n to R power n, and A inverse is a matrix from R power n to R. Okay, so then for every y belongs to R power n, there exists a unit x such that A inverse of x is equals to x. This is actually proof of this thing. Y mod of y max of this thing is 0, 1. A inverse of y is 2. Okay, this is giving that proof. If you have any doubt, just let me know. We'll again go through that. Okay, so one more thing that is very remarkable thing is let A belongs to R power n cross n such that min of magnitude of A is 0 and min of magnitude of A is nothing but min of max this mod of x is equals to 1, and this you can write these things. How you can write? How you can write this thing is min of magnitude of A is this thing. How you can write? If you keep this mod of x is equals to 1 and you're minimizing the range of Ax. Okay, so this thing you can write. Okay, so if it is 0, then what does this mean? The mean is the scalars that is making the linear combination of the columns of A should be equals to 0. It means that the scalar should be also be 0. Okay, so there exists x star such that mod of x star equals to 1 or A of x is equals to 1. So columns of A are linearly dependent. A is not invertible in that case when this minimum of magnitude of A is 0. Okay, now this is a very important thing. Let's quickly go through it. Let A is n cross n. I think I'm going very fast, but because since that is very long content was there. So it's very difficult to cover everything in 2 hours. So if you have any doubt at any point, you just stop me there. We will go through it again. Okay. So if let's resume it. Let A belongs to R n cross n, be an invertible matrix. Consider the set, this particular thing. The set is X such that mod of X is equals to 0. This is very, very important. Okay. So uh, this will cause actually a unit circle, okay, with origin as 0. Why? Because this is x1 square plus x2 square root over is equals to 1. Okay, so this is the equation of x1 square x2 square is equals to 1. So x1 minus x1c square plus x2 minus yc square is equals to 1. So xt and yc is nothing but 0. This is entered. Okay. So, under invertible linear function from R2 to R2, what does the unit circle transforms to? Just let us know what does the unit circle transforms to. Just think about this thing and type in the chat box. So, what is this transforming? So, if you just see the inverse of this transformation of the inverse, so if we represent this as y1 y2 that is belonging to R2, such that y1 y2 is nothing but a of x1 x2, that is a transformation. Okay, Manish is telling unit circle only. Okay, so under linear transformation, are you sure that every case it will be unique? Unit circle. Okay, let's see. Okay, so x1 x2 you can write it as a inverse of a y1 y2. That let's represent a inverse as b. Okay, so b you can write as a b1 transpose b2 transpose, that you can write x1 is equals to b1 transpose y1, x2 is equals to b2 transpose y2. And we know that x1 x2 x1 square plus x2 square is equals to 1. So if you say this b1 as b1 1 1 b1, because b is actually the matrix of b1 1 b1 2 b2 1 b2 2, and this is actually b1 transpose, this is actually b2 transpose. Okay, and then finally you are writing y1 square plus y2 square is equals to some value, like finally whatever the y thing that you are getting, and after transformation you are writing it here. What you are finding, that is the equation of ellipse. See, this is the equation of ellipse. What we did exactly, this y1 is a of, this a is a linear function, okay, and you're transforming it. Finally you're finding the equation of y that you're getting it. So equation of y is nothing but the equation in a ellipse, equation of ellipse in r square. So what you're trying to get, you are transforming the circle to a ellipse with the maximum magnification, and this is a of x. This is a of x with a minimum magnification, major axis and minor axis. So you might know x1 squared plus a squared plus, this is, sorry, y1 squared plus a squared plus y2 squared plus b squared is equals to 1. This is the equation of ellipse. A maximum magnification, b is minimum magnification. Okay. So yeah. So we saw already this maximum magnification is mod of A inverse in the previous equation. Okay. So we can write this max magnitude of A divided by max magnitude of A. So later what you're trying to see, A by B is nothing but a K2 of A. So whenever you're transforming a circle to a what? To a ellipse through a linear transformation, you're getting this as a ellipse. Now, if you make this K2 of A as 1, then you can make sure the transformation is circle only. It is reserving the property. So how will it transform? So this A matrix in that case should be orthogonal. Okay. I hope this is clear. Okay. So again, we are seeing with example of rotator matrix. So how it is orthogonal. So Q is a rotator matrix that is orthogonal. Then if we're transforming with respect to Q, this is same. Similarly, if we're transforming with respect to reflector, this is also same. Okay. So I think, thank God we covered all the conditions. So condition matrix is the condition number we saw through our geometry. What is that? Then under invertible linear function, unit circle is going to a ellipse. In only one case, it is going to a circle to circle, that is orthogonal matrix. And what is condition number? Condition number is something maximum magnitude of A divided by minimum magnitude of A. Okay, I hope this is clear. Now we will see quickly go through the questions. Now just let calculate quickly. What is the Frobenius norm of this matrix A? This is last year problem. We have how many participants? 1, 2, 1, 2, 3, 4, 5, 6. Okay. So anyone? Okay, anyway, you can calculate.
Root 6.
That's very great. Okay. So Lakshmi told this is a root 6. Okay. So answer is also root 6. Cute. Great. Okay. Moving to the next question. What is the answer of this question? So the question is, let A is this matrix, we are square invertible matrix whose condition number is denoted by this thing, which of the following is false. Okay. False is there. Tell me. A, B, C, D. Okay, so Guruswami told D. I think everyone will agree with that. We just now saw the property of this condition
D.
number. Okay, that's clear.
D is
Yeah,
false.
yeah. So moving to the next question, find the 2 norm of A. How will you calculate 2 norm of A? How will you calculate 2 norm of A?
Hello, madam.
How Manish, tell us.
How it is the answer for that mean margin, the maximum?
Okay, yeah,
Okay.
sure. So in that previous example, we saw this circle was transforming to ellipse, right?
Ellipse. Yes.
And in that ellipse, uh, we saw that this maximum magnitude was there and minimum magnitude was there. So maximum by minimum, that is A by B, was there. Okay. So that is given by max of magnitude of A divided min of magnitude of A. That's given by A by B. Okay. This is actually the value of condition number. So this is wrong, right? This is opposite.
Yeah, that is what I answer. I was confused. B should be the answer.
Yeah.
B is true. B is the only option that is false.
It's written here
D.
false.
Okay. Okay. Then it is D.
Yeah. Just D. Now tell me the answer for 3.
Manish, request you to please mute your mic.
Pardon? Yeah.
So you can calculate 2 norm of A, that is Guru Swami is telling C.
How
Yeah, Viveka. Uh, So okay, you all can calculate two norm of A. The norm of A is nothing but a Frobenius norm here only. You have to calculate the sum of 1 plus 1 plus 1.
Is 2 norm the same as Frobenius
No,
norm?
no, no, two norm is not same. This,
Then how come it's same here?
wait.
Two norm is actually taking one column and adding like that.
You are multiplying with the one column with the other column.
Okay.
Acha, yeah, that is induced now. Okay, okay, so sorry. We have to calculate. Okay, so sorry. I also get confused. The C, we saw the two norm for a matrix thing is max of x not equal to 0, A of x divided by x. Okay, we have to calculate like this. Okay, so 0 minus 1, 1, 0. This is x1, x2. This is nothing but x1 square plus x2 square. Okay. So this is x1 minus x2. Okay. Square plus x2 square. This is x1 square plus x2 square. x1 square plus x2 square. I hope this is clear. Okay. This is 1. Using induced norm only we have to calculate.
How
Yes,
did you
ma'am.
get the numerator to be norm of x1 and minus x2?
You
Column.
multiply with this thing. So this is x2. Sorry, this is x1. So yeah, I think it is clear now.
Ma'am, I have doubt,
Yeah,
ma'am.
yeah,
In Frobenius method is there, na, ma'am?
yeah.
How we related on UV orthogonal matrices on order n, any order
Wait.
orthogonal matrix.
What you are asking? Frobenius norm is actually the norm of vector of A. Suppose this A is there, okay? A is a many matrix. A11, A12, A1n. So okay, A2, AN1, ANN. So what you're trying to do, let's see vector of A is nothing but A11 to AN1. And these all goes on. You're appending first column here, then second column here, second column, first column, and last column. Okay. Then summing the all values, okay. This is okay. A11 square means first column square plus second column square to all n column square. This is Frobenius norm. Okay. And we saw this is following the matrix norm property. Okay. This is following matrix norm property. But if you try to find any norm for any vector, suppose 2 norm, p norm, any norm, so this we found it. And this is also following all the matrix norm property, including submultiplicative property, including triangle inequality, including every property. It is following that. Okay. So how it is? I hope this is clear, Viveka.
Yes, ma'am. But orthogonal matrices.
That is different. This is
that,
we are talking about norm now. The orthogonal things that we are talking about when we saw a circle transform into an ellipse, then in that case it the maximum and a minimum divided by was 1. How it was 1? Because we got transforming using a orthogonal matrix. In that case only it was 1. Otherwise it is not 1. Okay. So that because all the columns of this Q is orthogonal to each other and also orthonormal in some cases. We will see some examples. This is a question related to norm. If you have some problem related to QR decomposition, then we will see that also. Okay. I hope this question 3 is clear to all of us, all of you. You have to solve like this.
There is another way to solve it, no? That true norm of a matrix is root of A transpose A. That was taught in lecture 3 or something, no? True norm of a matrix.
You can calculate. Yeah. But when this sir taught about this thing, I think he'll teach in the next thing.
In one of the earlier lectures, no? Lecture 3 or so,
Oh,
week
okay. The
3 or so.
previous lectures. Okay. That is also one way. You can verify with that also. That is one of your exercise also. That can be an exercise. But that thing, I think that will be A transpose A root over A transpose A, you're telling, right?
Square root of A transpose into A.
Yeah. That will also work. Okay. But just now what we studied, we followed it. That is also following the same thing.
Okay, agreed. Yeah, we'll move on to the next question.
Okay, we can move. Okay. So, moving to the next question. So, answer is also there. For a rotation matrix, L2 norm is always equals to 1. Since the matrices have orthogonal columns, this is telling that this is a rotation matrix. Okay, I think Viveka, you were also telling that this is a rotation matrix. My intuition is this is a rotation matrix. How it is rotation matrix? It is because it is rotating. What is rotation matrix? You have this x vector. You are rotating with theta in anti-clockwise direction. You are getting some y vector. This rotation that is causing from x to y. So y is this a of x. Okay. So this is rotation matrix. So all the rotation matrices will have the norm as 1. Okay. So sorry. Now let's solve question number 4. Let's solve this question number 4. How to solve? We know all. I'm just waiting for 1 minute. Please tell anyone.
1/3.
1/3. How did you solve this? Simple condition number, right? Condition number of A should be greater than equals to 1. So suppose this max of A is x divided by 3 should be greater to 1. So x should be greater than 3. What we are telling answer is 1 by. So Guru Swami is telling C. Okay. So sorry. This is max of. Yeah, this is max of A. Okay. So since max of A is greater than equals to 3, so we know that max magnitude of A inverse is nothing but 1 upon max magnitude of A. So 1 upon 3. Okay. So answer is C only. Okay. Anyone have doubt? How it is C? We are using the condition number property, and then we know that this is max magnitude of A. Then I'm just making the use of this property. I'm sure the answer is C. Okay. C. I also used it. Okay. So if you have A as orthogonal matrix, then this is true only. This is very straightforward. Now let's solve this question number 6. Which of the following formula correctly defines the induced norm of a matrix A? Then?
C, man, directly.
Okay. Very good. So everyone is telling C because just now we saw that. Okay. Why? If everyone had doubt, we can follow the properties of this matrix norm. What were the properties? 2 properties that we had just discussed. This norm value should be greater than equals to 0.
Is induced norm the same as max mag?
What?
Is induced norm the same as max magnitude? Is induced?
No. Max magnitude. No, it's not same. But yes, in some possible cases it is yes also. What is max magnitude? If you see this max magnitude, we are what we are doing. We are maximizing norm of ax divided by norm of x. Okay, maximizing such that x not equal to 0. But yeah, it is same only in case of norm 2. Okay, the formula is same. Why? If
Formula
you
is same in case of norm
ha
2, but in other case,
it is not same because you are that induced norm is defined for particular norm, right? And if you see this particular thing also, let's see that thing also. If you have x vector, okay, you are magnifying it with respect to ax. That is an image of x, because uh,
oh,
this a is nothing but a linear transformation or linear function. Okay,
okay,
and then you are maximizing with respect to x. So what you're doing, the length, you are trying to find the length of ax, the maximum length of ax that
okay,
x is causing. So in two
okay,
norm it is same. Okay, moving to the next question. What is the condition number of orthogonal matrix? That is one only. Okay, everyone knows that. Not
Ma'am, then what is any 2 cross or 3 cross using one norm? How we check condition number?
what?
Any matrices?
Uh,
Any matrices like 2 cross 2, 2 by 2 or 3 by 2, using one norm, how we can check condition number?
uh,
I think what he asked, induced norm in the case of you know other other norm dimensionalities, not only A2 norm, other norms. How will what is the definition of induced norm? Is that what he's asking?
yeah. We
That's
saw
what I.
no. We saw max of x not equal to 0, a of x p divided by a of x. Sorry, x. We saw no. This is
Okay, okay,
p. This is in general formula. Viveka, this is in general formula. You can calculate using this thing. And one most interesting property is if you have xy plane. Okay, this is 2 norm. This is 1 norm. This is infinity norm. 1 norm. So, okay, I'll give you this here to homework for you. Just try to plot all the norms in one graph and come in the next class. Then we will see some of the intuition.
Ma'am, like one example, A is equal to 1, 2, 3, 4.
Okay.
Then what is matrix? What is the condition number?
A is equals
A
to
is equal to 1, 2, 3, 4. X
1, 2, 3, 4. First of all, we cannot
means
define for
matrix 2 cross 2.
non-invertible matrix, right? It should be n cross n invertible matrix only.
Ah, okay, ma'am.
Okay. The condition number is
Using one
defined for
norm.
only n cross n invertible matrix.
Yes, ma'am. Take one example and solve it.
Okay, let's see. Taking only uh 1, 2, 3, 4. Okay. Now let's see one norm. Okay. So one norm, how will you calculate? Max of x not equal to 0. A of x. A of x is what? I'm just taking one. One, two, three, four. A is equals to 1, 2, 3, 4. Then ax is equals to what? It is x1, x2. Then x1 plus 2x2. Then it is 3x1 plus 4x2. Okay. And then what is the norm of ax? One norm. What is the norm? This is x1 plus 2x2 mod plus 3x1 plus 4x2 is mod. Okay, and x norm, one norm is x1 plus x2. Okay, now we can write this one as 4x1 plus 6x2. Okay, now 4x1 plus 6x2 divided by x1 plus x2. Now we have to maximize it such x not equal to 0. That's a straightforward problem. Can we do that? This is how will you maximize it?
Thi-
Yeah.
This is condition number, ma'am.
What you asked me to calculate? Two norm.
Condition number.
Okay. So you asked me to calculate condition norm. So yes, this is I calculated for one norm. I calculated induced one norm. Or you induced one norm. So condition number is simple. K2 of A, simple mod of A. Can you do that? Just have to two norm of A. First of all, you have to calculate two norm of A, then multiply with the two inverse of two norm of A. How will you calculate the inverse of A? A is nothing but 4 1 minus 3 minus 2. Now calculate A. This is A inverse. Just multiply with this. Got it, Viveka?
Yes, ma'am. Yes, ma'am.
Yeah, this is the formula that you can directly get it. Okay. Why can't we define condition number with respect to other norm other than two norm? Because in the derivation we saw that uh, we've verified with respect to two norm only. If you go back to the derivation, I think if we want to define, we can define. Let's see if we can define or not. But I don't know why it is not defined. But if it is defined in a particular way, then we have to accept that this is defined in a particular way. So if we go to the this is because Guruswami, because we are more comfortable with the two norm, and also we saw some multiplicative property to be applicable over two norm easier than other norm, and also yeah, that the answer will come from if you plot all the norm pictures in one graph. That we will discuss in the next class. Yeah, Lakshmi.
Ma'am, for any square matrix, like for any 2 by 2 square matrix, can we write the inverse as for the left diagonal, interchange the elements, and for the right diagonal, change the sign of the elements? Will that easily give us the inverse of any 2 by 2 square matrix? Like we do?
Yeah. Divided by determinant of A that you forwarded.
Okay.
Yeah, that
Fine.
was a trick, like easy way to calculate. So okay, we proved it with respect to this particular thing. You can also take other norms here. Okay. But the thing is, the error, the here definition of error will also be different, right? Error will be defined with respect to different norm. And generally the two norm represent the magnitude. Okay. Even if you visualize it from here, if you have this particular point, x1, y1, okay, this particular thing is actually two norm, that is showing the magnitude of 0 to particular point. Okay, this distance is given by two norm, so that's why we are defining with respect to two norm. I hope this is clear up to this point. So we will resume the next class as we are running out of the time. So thank you so much for joining, and thank you so much for this interactive sessions. I really love to answer your questions, and yeah, please register for the exam as soon as possible. And yeah, if you have any doubt, you can just reach out to me over email ID. I'm just sharing that also. So thank you so much. If you have any issue, just let me know. Yeah, Manish, tell me.
Madam, can we have the questions covered in the previous week assignment sometime?
Okay. I'll be anyway sharing in the sheet.
Or their solution is sufficiently given so that we can refer solution
Okay,
only?
but in every week, actually, I have solved the questions in the class discussing with the students only. So, okay, I'll share that. I'll share that.
Okay. Thank
Okay,
you.
Manish. Okay.